Okay, let's get started. I think we have a quorum. All right, so this session is going to have two talks about applications. This time it's really about applications. And so, yeah, our first speaker is Trisha Datta, who's going to talk about image provenance. So looking forward to your talk, Trisha.
Thanks, Dan. Thanks. Just a quick plug before I begin. So at Stanford, we have a theory seminar every Thursday. There's a half hour for lunch and then a half hour for a speaker to give a talk. So if you're around this summer and you have any interest in giving a talk at Stanford to kind of a broad theory audience, please just email me and we can get you on the schedule. All right. So today's talk is going to be kind of about using zk-SNARKs for real-world security. So I guess you can think of it as using zk-SNARKs for applied cryptography. And that's my one contractually obligated zk-SNARKs joke. But really what we're going to be talking about is this issue of image provenance. So kind of the main motivation for this work is this idea that it's become increasingly difficult when you see a photo online to know where this photo actually came from. So this slide is showing how kind of scary good AI has gotten at generating photorealistic images. And I'm sure we've all had this experience of looking at some kind of image online and having this doubt or this thought of like, is this actually a real image? Was this taken by a real camera? Or was it just generated by an AI model? And you know, even if we know somehow that it was actually taken by a real camera, we also have no way of knowing when and where this photo was actually taken. And it would be really nice if we could have some kind of formal guarantee that the photo that we're looking at online, you know, was indeed taken by a real camera, and if so, where and when it was actually taken. So one proposed solution to dealing with this is the C2PA, which is a content provenance standard. And this was developed in conjunction by a bunch of different companies, so tech companies like Sony and Microsoft, as well as news organizations like the BBC. And the idea is that every camera would be equipped with an embedded certified signing key. And in fact, there are a bunch of different camera companies that are actually either producing such cameras or in the process of beginning to produce such cameras. And Leica actually is storing the key in a hardware enclave to kind of make it extra hard to extract. And the idea is whenever one of these cameras takes a photo, it would digitally sign the photo along with some metadata about the photo, so things like location and timestamp. And then if you ever encounter this photo in the digital wild, you can verify that it was taken by an actual camera and verify its metadata just by verifying this digital signature. Yes?
Do you know if all of these or some of these or none of these have a per device secret key versus a global secret key?
It is a per device secret key, okay. Yeah. And the secret key is kind of certified by the camera company.
Yeah. To what extent is this signing process tamper-proof? Like if you mess with the camera's hardware, how difficult it is to get around this signature?
Okay, yeah, I mean, I guess that's definitely, as I talk more about C2PA, there are definitely kind of challenges with it. So I guess that depends on the particular camera. I don't know off the top of my head kind of how hard it is to mess with the hardware. Again, like Leica is putting the key in a hardware enclave, but that's definitely, you know, securing the physical device is definitely another, it's something to be concerned about and be vigilant about, yeah.
For your talk, the assumption is it's tamper-proof.
Yeah, for the talk, the assumption is it's tamper-proof, yeah. All right, so the C2PA kind of, I guess maybe originally the people who were really interested in it were news organizations. They were really interested in proving kind of the authenticity of the photos used in their articles. But nowadays, it's not just news organizations who are interested in kind of using the C2PA to attest to the provenance of their images. So actually, DALL-E 3, every single image that it creates, comes with a C2PA manifest. And you might be wondering, well, why would a generative AI company be interested in producing a C2PA manifest for its images? And one reason we can kind of think of is they don't really want to be accused of creating illicit or explicit content. And so if someone says, hey, DALL-E 3 created this unsavory image, then OpenAI can say, all right, show us our signature on that image to prove that we actually made this.
I have trouble understanding the adversarial model.
Yeah.
When I'm signing the photo,
yeah.
I could spoof both location and timestamp.
Yeah.
So the adversarial model is like, I don't want to be attributed with something that I did correctly.
So I think the idea is we're assuming that you can't spoof location and timestamp on the camera.
Huh?
Okay.
Yeah, that is kind of the assumption of the C2PA. Yeah.
Yeah.
You'll talk about that.
Yeah, I'm going to get to that in the next slide. On the next slide, I'm going to talk about all of the issues that you might be potentially seeing with the C2PA.
Okay.
So maybe kind of the first attack that you might imagine is this picture-of-a-picture attack. So say you generate some image with AI, and then you take a C2PA camera, and you take a photo of that photo. Then now you have a signed image of this AI-generated photo. All right, and you might think, okay, well, maybe we could have verifiers run some kind of filter that can detect if the photo that they're looking at is actually a picture of a picture, but then also maybe attackers can get around this filter, and there's actually a paper at Usenix this year about doing just this. And even beyond this, there are a bunch of other potential issues. So one thing that we have to figure out how to deal with is key extraction and revocation. So let's say that you have some camera with this key, and the key gets extracted. Then you want a mechanism to kind of say we should no longer trust any images signed by this compromised key. You also have this privacy issue now because there is going to be a per camera key, and so that's going to basically identify the camera that's taking a photo. And so, what if you have a situation where you have like someone taking a photo in a demonstration in a place where there's an oppressive regime, and now you want to verify the signature on this photo, well, you're actually going to have to identify the camera that's actually taken this photo. So that's not really great. One way we can maybe get around this is with group signatures, and so in that case, basically what you would be verifying is not that a particular Leica camera took a photo, but just that a Leica camera took a photo. Also, as you mentioned, there's this issue of can the person who owns the camera do some GPS spoofing and then get the camera to attest to the fact that it took the photo in a place where it didn't actually take the photo. So there are a whole bunch of issues, but with your kind and generous permission, I'm going to ask that we ignore these issues for the rest of the talk and instead focus on a different issue with the C2PA. And so I guess maybe you're uncomfortable with ignoring. I would just say that we can look at these issues as perhaps opportunities for future cryptographic work and kind of securing various parts of the C2PA pipeline. All right. So the part of the C2PA pipeline that I'm going to talk about today is this issue of, there's also this other talk if you're interested in learning more about some of kind of the issues with the C2PA. But what I'm going to talk about today is this issue of how to handle post-processing. Yes?
It's not about the issues.
Okay.
I'm still curious about the motivation for AI companies to provide this manifest.
Yeah.
So is it the case that right now it's a volunteer basis, or do you know if there is some upcoming regulation to force AI companies to do this? Like
I do believe right now it's just a voluntary basis. I don't know of any upcoming regulation. I guess you could imagine like a utopian or maybe dystopian world, depending on how you think of it, where all content on the internet has some kind of verifiable chain of provenance. But yeah, right now it's just voluntary. And I do think maybe the main reason is that they don't want to be accused of creating content that they didn't actually create. Because I think maybe I don't know if there are rules about not like producing explicit content, but they probably don't want to be producing that kind of content.
And do you think it's also dystopia to have content provenance for everything?
I don't know. Maybe that's a conversation we take offline. Yeah.
So California has a regulation that starting 2026,
Okay.
people will have to pay for the mark.
Sorry, can you say that again?
California does have a regulation that's already passed that things will have to be worth of art, and companies will provide either a public or API caching.
All right. So for the rest of the talk, we're going to be talking about this issue of post-processing, which is basically the idea that usually before photos are published online, they're edited in some way. And so if we're talking about newspaper articles, then at minimum, photos are usually downsized, and this is kind of just to decrease loading times. But there's also kind of a variety of other edits that might be applied to a photo before it's published online. So there's actually this list of what the Associated Press calls allowable operations. These are things like cropping, grayscale, blurring, basically things that aren't going to change the semantic meaning of a photo. And the reason why this post-processing kind of puts a wrinkle in the C2PA, as I've described it, is that in order to verify digital signature, you need access to the thing that was signed, right? So if all you have is this post-processed photo and a digital signature on the original photo, well, now you have no way to know that this post-processed photo, you have no way to verify the signature because you don't have the thing that was signed, you just have an edited version of it. And so The way that the C2PA proposes dealing with this is kind of just by introducing a trusted third party. But of course, that's not really ideal, and we would like to do better. And the way that we're going to do better is by using zk-SNARKs. All right. So I'm not going to redefine zk-SNARKs, because I hope by this point in the workshop we're all very familiar. So what I'm going to do is I'm just going to kind of show you how our situation maps into like the language of SNARKs that we've been using so far. So the editor, who is going to be the prover in our situation, they're going to have an original photo as well as a camera signature on the original photo. And you can think of this as the witness. Now, the laptop or the verifier, what they're going to have is this public edited photo. And we're also going to assume that they have access to the list of operations applied to this photo. So things like blurring, resizing, et cetera. And this is going to constitute the statement. So now, again, what the editor wants to convince the laptop of, or the verifier of, is that this edited photo is actually derived from a signed original photo. And to do that, it's going to create a SNARK that's going to prove three things, basically. So one, that it has a signature on an original photo. Two, if you apply this list of public operations to this original photo, you get this edited photo. And three, that the metadata of these two photos are the same. Okay? And something I'm kind of leaving out here is the public key and where that all fits in, but I'm just going to, for simplicity, we're not having it in there. But you can also imagine that this proof might include some kind of proof that this public key was actually certified by the appropriate camera company. Okay, so you might, and yeah, so the laptop can just verify this SNARK and then show the metadata to the user. So you might be wondering, why do we actually need real ZK? And kind of the answer is, it depends on the operation. So if you're just resizing, you might not really need a zk-SNARK. But if you are cropping out sensitive information or blurring out sensitive information, then you might actually want the ZK property to kind of preserve the privacy of whatever you're editing out.
Also the metadata, maybe some of it want to leave out.
Sure, yeah, that's another great point. Yeah. Yes?
Is it has to be that the ops are part of the things that the verifier knows, or they could just as much be part of the witness? Like I would not see any reason.
You probably could hide them. It will be more efficient to not hide them.
Oh, okay.
But yeah, you could probably hide them. Yeah. All right. So for the rest of the talk, I'm going to kind of just try to give you a brief overview of how exactly we prove these three things. I'm actually only going to focus on the first two. The third is not so interesting. So let's talk about the second bullet here. So given some public edited photo and a list of public operations, how do you prove that you know some original photo such that if you apply these operations to the original photo, you get the public photo? And so in 2016, there was this work called Photo Proof by Neve and Tromer, where they basically did exactly this. They created these photo editing proofs for photos. And this was really great work as a proof of concept. But unfortunately, it took them a few minutes to create these proofs for relatively small images, so 128 by 128 pixels. And the cameras that I mentioned a few slides ago, they're taking pictures that are on the order of 30 megapixels or 60 megapixels, so several orders of magnitude larger. And proof generation time is going to kind of scale with the size of the input. And so for a realistically sized photo, this just isn't going to be practically feasible. The good news then is that there's been an explosion in SNARK technology. So over this past week, we've seen a lot of the theory developments. And it's actually funny because this workshop is called 10 years later. This paper is from a little less than 10 years ago. But now we're going to see how kind of the theory improvements have led to actual practical concrete achievements. And so specifically, we can actually use new tools to prove much larger statements. And so the tool that we use is called Plonky2, and I think on Monday we talked about how if you want to get a SNARK, what you can do is you can take your favorite information theoretic proof and then combine it with some kind of cryptographic object. So here we're using the Plonk PIOP, which is a PIOP for proving the correctness of arithmetic circuits, and then we're going to combine it with the Frye polynomial commitment scheme. And so the way that we use this to prove photo edits is we basically just design an arithmetic circuit that corresponds to your favorite photo edit. And we want it to be designed such that if you plug in your original photo to the circuit, the output is going to be your edited photo. All right, and then we can just use the Plonky2 library to create a SNARK for this. Now, the results that we get is that we can actually create these editing proofs for a variety of different edits for realistically sized images in a few minutes. So that's like a really great improvement. The proof size is about 100 kilobytes, which is kind of big, but if you think about these photos, which are on the order of megabytes, that's really not that bad. And we can always actually shrink the proof with recursion. And the really important thing here is verification time is also quite fast. So this is an example of, we actually really care about succinctness because, ideally we want these proofs, every time you're looking at one of these photos with one of these proofs, you want to be able to verify the proof, and so you want that verification time to be really fast.
What's the cost of the clear text computation, of resizing, cropping? Like, what's the slowdown factor here?
Sorry, I couldn't hear you over the construction.
Yeah, 4 minutes it takes you to generate a proof. How
Yeah.
much does it take you to do the same operation without a proof?
I mean, it's probably pretty instant. Like if you imagine on Photoshop, if you resize, it takes, no time, right? Yeah.
No, just in terms of the ratio, the slowdown factor, can you estimate it here? Because
I guess I don't, like if you think about applying an edit in Photoshop and resizing, that's pretty instantaneous. I don't know, like off the top of my head, how many milliseconds that takes, but yeah, this takes 4 minutes and that's pretty instantaneous. Yeah. All right. So the next thing I want to talk about is this first bullet here, which is how do you prove that you have a valid signature on an original photo? And this actually turns out to be the hardest thing. It's the bottleneck. And the reason why is because when we sign something in practice, usually what we do is we hash the data, and then we sign a hash of the data. So proving that you actually know a signature on something, what that amounts to is proving that you've honestly hashed the data, and then that you've honestly signed that hash. Okay? And the thing that makes this really hard is the thing that we're hashing is really big. It's like 90 megabytes, for instance. And so you might hope that we could actually create this kind of proof using a standard hash function like SHA-256. Unfortunately, this is just going to be impractical for something as large as 90 megabytes. And maybe the intuition as to why is we have to basically express the thing that we're proving in terms of things like arithmetic circuits, which are just a bunch of multiplication and addition gates. And so if you've ever seen the SHA-256 specification, it's not easily expressed in multiplication and addition gates. Okay, so there's just going to be expressing it in that way is just going to be very impractical. Now there are SNARK-friendly hash functions. So these are hash functions that are specifically designed to being amenable to being expressed in things like arithmetic circuits. Poseidon is an example of such a hash function. Unfortunately, 90 megabytes is still too slow for us to prove that we've honestly hashed something this big with Poseidon. And so what we are doing is we're proposing two different methods, and they both basically work by changing the hash function that is being used. So the first method is we use a lattice hash. And this turns out to be really great for the camera, for the signer, because computing a lattice hash is relatively quick. It's also pretty great for the prover, and kind of the intuition as to why is a lattice hash is basically just a matrix vector multiplication. And if you think about expressing that in terms of an arithmetic circuit, that's like pretty easy, pretty straightforward. And so that's why we can actually do this or prove this pretty efficiently. The second method that we propose is instead of signing a hash, we're going to sign a polynomial commitment. So somehow encode the original photo as a polynomial and then sign this polynomial commitment. And this actually turns out to be a little bit expensive for the signer, and I will get to that eventually, but it actually turns out to be great for the prover. So let me just go into these two modes a little bit more in detail. So for the
You made a distinction between the prover and the signer?
Yes. So think of the signer as the camera, and the prover is the editor, the one who's making these edits, yeah. All right, so the first method when we're using a lattice hash, hopefully this is gonna look very straightforward because it's basically what I've just been talking about the whole time. So the camera is gonna take a photo, it's going to sign a hash of this photo, in this case a lattice hash of this photo. It's gonna send the signature and the original photo to the editor is gonna make some edits, and then the editor is gonna sign the public photo and proof pi, and it's also the list of operations, but I've omitted that. And this proof pi is basically going to prove the validity of the edits and also the validity of the signature. Now, the second method, the reason why I presented this method is because the second method is going to be a little bit different. So this first method should look very familiar and standard. That's basically what I've been talking about the whole time. The second method, where we sign a polynomial commitment scheme, we're going to tinker with this a little bit. So again, there's going to be a photo taken by the camera. It's going to be signed. Again, this time we're just going to encode the photo as a polynomial and then commit to this polynomial and then sign that commitment. We're still going to send the original the original photo and the signature to the editor. But now what the editor is sending to the verifier is a little bit different. So it's still going to send the edited photo. It's still going to send a SNARK proof pi. But actually, this proof is only going to prove statements about the edits now. And we're actually just going to directly give the polynomial commitment and the signature to the verifier. And the verifier is going to separately verify the signature and this proof. OK? So hopefully you're looking at that and you're thinking, that looks a little bit fishy, right? Because what I'm saying now is, now this proof pi is only proving statements about the edit, OK? So it's basically proving that I know some original photo, let's call it orig prime, such that if you plug in this photo into this editing circuit, you get this public edited photo. And what I'm saying is the verifier is going to verify this Planck proof and also verify this signature on this polynomial commitment to an original photo. But as I've described the scheme right now, there's no way that the verifier can actually link the witness that we used in the Planck proof to whatever is committed to in this polynomial commitment, right? So as I've described this to you now, like we have a signature on something, and we have a proof that has a witness, and we really want to know that the thing that was signed was actually the witness, but right now there's no link between those two. So we have to somehow link these two. And the way that we do this is actually by using non-black box use of Planck. So what I'm going to try to do now is explain Planck in the least amount of detail possible so that you understand what we did. And so basically what Planck does is it takes the arithmetic circuit that you're trying to prove correct execution for. In this case, it's our editing circuit. And it's going to encode the execution tableau as a polynomial. Okay? So basically, it's going to encode the witness values, the witness input values, the internal wires, as well as the output wires as a polynomial. So kind of the thing to know is that some evaluations of this T of x will encode the witness orig prime. Then to create a Planck proof, what happens is the prover is going to compute a polynomial commitment to this tableau polynomial. And then what it's going to do is first it's going to prove that all of the gates in the arithmetic all of the gates in this tableau are locally satisfied. So every time there's an addition gate, the two inputs should sum to the output. Every time there's a multiplication gate, the two inputs should multiply to the output. And it's going to do this locally for each gate. And this is going to be with respect to this commitment T. And then what it's going to do is it's going to prove that the wiring in the tableau is correct. So what does this mean? Well, imagine you have some gate that has an output that is an input to two other gates. So in the previous step, we verified that those two gates are locally satisfied. But what we now need to verify is actually that those two inputs match, right? And so we're also going to prove correct circuit wiring with respect to this polynomial commitment. And kind of the key, cute innovation or observation that we make is that all of this works even if the tableau is committed via multiple polynomials. So kind of in your standard run-of-the-mill Planck, you just have this one tableau polynomial that encodes the witness values and the internal wire values and the output wire values. But if we actually had separate polynomials encoding these different types of values, then with just a little bit of modification, we can still create the same type of proof. All right, so, sorry, do you want to? OK. So basically, specifically what we're going to do is we're going to have the input values being encoded by this signed polynomial commitment here. And we're still going to have another polynomial that kind of captures all of the other values that we need to encode. And then we're going to create this proof, this Planck proof, with respect to both of these polynomials now. All right, so it's going to be verified with respect to this signed polynomial here, as well as another polynomial created by the prover. And so that is what's kind of link the signed polynomial commitment that we have from the camera to the Planck proof. Okay, yeah.
I'm missing something, but isn't the abstraction that you're trying to use here a commit and prove SNARK? That essentially the camera is performing the commitment to the witness, then signing the commitment, that will be passed along the chain. Yeah. And then in particular, Planck can be adapted to fulfill the interface of a commit and prove SNARK.
Yeah, I think you can kind of think of it that way. We're just kind of, I guess you're familiar with Planck, we're going to kind of use the permutation argument in a specific way to do that. But yeah, just in general, you can think of it like that. Yeah.
But maybe, sorry, maybe I apologize. I don't understand the problem with the, because in principle, if you do a snark that you know the value committed by this PCS commitment was modified in this way, what is the problem? You're saying this original is not equal to original prime. I'm not sure.
So you're not. Why are we doing this whole linking thing? Is that?
Well, this thing, why this problem of the previous slide? They say,
okay.
What if original is not equal to original prime? I just don't. Isn't it?
You'd have to open the commitment within the snark and prove openings as a circuit, which is what you don't want.
So you're saying you could do it, but you, I think. So,
yeah.
So what is the statement that you are proving in a non-black box way? You're saying the statement is weaker?
The statement that we're proving is that basically what this proof is going to end up proving is that this orig prime, if you plug this into the circuit, you get this edited photo. So without this kind of, without messing with Planck, all we know is that all this proof, like if this is just a standard Planck proof, all it's saying is that there's some original photo where if you apply these edits, you get this edited photo. But you don't know that that original photo is this one contained in this polynomial commitment here.
But you showed it was signed, right? You're saying there was something signed by the camera for which this is a transformation. That's good enough, right?
But
you're ignoring signature, you're not.
Yeah, this Planck proof is not proving anything about a signature.
Oh, I see.
Yeah, that's the whole thing, is we're taking, so in the lattice hash method, you do have to prove something about the signature. And now what we're saying is we're not doing that anymore. We're just going to have the verifier verify the signature itself. But now you need to know that this thing, that the thing that was signed is actually the thing that was input into the editing circuit.
So you're saying the proof now is not tied to the signature?
Yeah.
Okay.
Yeah. Any questions? Okay. I think I'm running out of time, so I'll just say very quickly what we just said, that this takes the signature verification outside of the SNARK circuit. The kind of drawback is that computing a polynomial commitment is really expensive, and normal commercial camera can't do it. So right now we're thinking that this kind of approach might be suitable to AI-generated images. OpenAI definitely has enough compute power to do this. And we're also looking at ways to maybe outsource this kind of computation.
How do you compare, let's say, an iPhone versus a camera? Would an iPhone be able to do that?
Yeah, I guess we haven't really thought about that, but it seems...
Probably not. It's probably too hard for iPhone.
Yeah. Oh yeah, I'm sorry, I don't know if I said, but Dan and Vinny are my collaborators. Maybe I forgot to say that at the beginning, sorry. All right, so we talked about how to prove everything, and I guess kind of the overall takeaways is that kind of due to the explosion of theoretical SNARK research, we can actually use SNARKs in practice these days, and a lot of the applications are for blockchain, but hopefully what I've convinced you of, there's also a lot of really cool non-blockchain applications. And then kind of getting back to the C2PA and all of the opportunities there, I think there's a lot of cool potential for cryptographic solutions there as well, and so that's a very interesting road to explore. And this work was presented at SMP this year, and the paper is here if you're interested. And that's it.
Yeah, please.
Yeah, coming back to the commit and proof thing, right? So you mentioned you're using this permutation argument, but that leaks evaluation points, right? Which normally in Planck isn't an issue because we can just add, hiding values. But you're doing it with the original commitment that the camera generated.
Yeah.
So if I do some, this is a bit of a pathologic scenario, but if I do a lot of edits on the same photo, that kind of breaks the zk-SNARK property, right?
I see. Yeah, I think there probably would have to be like a little. It seems like you could get around it, but yeah,
because you can do unbounded. Like you don't have the guarantee on like how many edits somebody's going to do to one photo, right? So you don't know how many blinding values to add.
So we're not actually opening any evaluation, like.
But you do a permutation argument, right, on the PCS orig, and
so you're saying if you open it again and again and again. I see. Yeah. That may be. Yeah, maybe we'd have to have some kind of limit on edits or some kind of way to hide.
Well, this is going to be for a single editor.
Yeah.
So this will be for a single editor. You can do multiple edits, but a single proof.
Yeah.
I guess but like you don't like as soon as you sort of like. Yeah, I guess like if one person were to do a lot of proofs, but I mean again like I think the number for such a large image will probably be pretty insane.
But if it is one person, they can choose how many blinders run. So for each new editor, you do a new, you know in advance.
Oh, right, but actually I don't think it matters if it's like, because I guess the point is it only, like even different people that have access to the non-hidden image, right? If two different people do like a number of edits and they both hide their own leakage, right? But they both have access to the raw image, then they contribute, like, you know, if you combine them, right? So I don't think you can prevent this by just adding blinding values, because you can have multiple people doing edits.
This sounds like it's a good topic for, well, let's take this offline.
You'll take this on, let's say.
Yeah, any other questions? All right, thank you, Trisha. Chavi, who is a postdoc at CMU. So Chavi was a student in San Diego, and actually Chavi is not a cryptographer. Chavi is a machine learning person.